All right, so today we're going to talk about, and kind of stemming off of Newton's first law, we're going to talk about the ideas of inertia and a property of matter called mass. So this is helpful to explain Newton's first law of motion, which states that an object at rest will stay at rest, and an object in motion will stay in motion. It's very easy to understand this in terms of an object being at rest. Okay, last section we talked about the idea of balanced forces. So let's say that I have something resting on a surface. If it's at rest, it's easy to see that it's at rest because the forces are balanced. Say I have the pull of gravity downward and the table supporting it upward. Those two forces cancel each other out. They're equal and opposite. Balanced forces will cause that object to stay at rest. And that makes sense because an object at rest, we typically wouldn't even see a force acting on it. It's somewhat difficult for us to think that maybe there are forces, but those forces that do act on it are balanced. Okay, now the idea then of Newton's second law about an object in motion will tend to stay in motion. What this states is that as an object, let's say that same ball, is now moving at a constant speed across the surface. This is the same thing as looking at something at rest. It's moving at a constant speed because the forces are still balanced. But it's very difficult to explain this because as we see something in motion, right, the state of motion we want to think is caused by something. Obviously, this ball was set into motion by something, but as it moves, is there a force required to keep it moving? So this first experiment was brought up by Galileo. Galileo said that if I take a ball and I roll it down a surface, so let's say it rolls down a ramp, hits a flat surface, and then rolls back up a ramp. Okay, as this ball rolls down, it's going to gain speed because of gravity, as we talked about. As it moves along the surface, assuming that this surface is frictionless, and this was the key thing, is that if we can take away one of those naggy little forces of friction that always tends to slow things down, if we were to take that away, as the ball hits this level surface, it's going to move at a constant speed. All right, so it gains speed due to gravity pulling it, then it's going to move at a constant speed. And what Galileo thought was if I put an incline similar to the first part on the other side, the ball would roll up and come to a stop. And what he wanted to compare was he wanted to compare the initial height of the ball here compared to the initial height of the ball at the end. And what he recognized is that assuming that there was no friction, whatever height I placed the ball in the beginning, it would reach that same height in the end. And he recognized that the ball has some oomph to it as it's rolling down the incline, as it reaches the surface. That's going to reach that constant speed, but it carries that oomph with it. And that oomph will drive it up the incline until gravity takes all that speed away. So looking at it, he said, okay, what if I extend this track? Let's say I lower the incline and give it more room to play. How would that affect it? And again, what he recognized is that the height at which it started always matched the height at which it ended. Okay, it got a little bit of oomph, and if I lowered it down, that means gravity didn't have that much effect on it, and it would go a little bit further down the ramp, but in terms of up the ramp, it would always go to the same height which it started. So following this, as long as I lower the incline, it's going to move further along until it reaches the initial height. So based on that, what if I didn't allow it to get up to the height? Let's say I took this second part of the track and made it completely horizontal. The ball obviously would gain speed, but once it got to this point, it would gain all the speed it possibly could, and assuming no frictional losses, what happens here is that this ball would continue to move. But again, as it moves, we still have gravity pulling down on it. It's still being supported by the surface, so notice the forces there are balanced. There's nothing making this thing move. It's moving on its own accord. Now, what he called that is when an object is moving on its own accord, we call that the idea of inertia. Inertia is a physical property of an object that always wants it to resist changes in motion. Meaning if something's at rest, it wants to be at rest. If something is in motion, it wants to continue in that motion. That is a natural property that all objects have, where we want to resist any sort of changes in the motion that we experience. Okay? And that's kind of what's going on here is the ball, if we set it into motion, the only thing that's going to stop it from doing what it does is if I were to place something in its path that would cause it to change. Otherwise, this ball will continue to do what it's doing. So this idea of inertia is thinking about something's resistance to motion. It's easy to think about this in terms of something being at rest. So if I want to push something, it's going to be harder to move if it's made of more stuff. It's going to be lighter and easier to move obviously if it's not as made as much stuff. So what really gives an object that property of inertia is its mass. So mass is inertia, and this is what it was first thought of, is that mass is simply a measurement of how much inertia an object has, how much resistance to any change in motion. Now when we think about that resistance, that is due to something having a lot of mass, and mass is simply the amount of matter something is made of. Think of matter as the stuff we're made out of. So if you're made out of more stuff, you are going to be more massive. You're going to be harder to move. Okay? Take, for example, me pushing a chair. It's very easy for me to push a chair in general because a chair is not that massive. But if all of a sudden now I want to take, say I put somebody in the chair and now I want to push or pull them. Well, now it becomes more difficult because by adding the person, I am adding more mass to that object, making it hard to move. Same thing in reverse, or if you think about something moving, if I have something that's in motion, it's going to be harder to stop it or change its motion if it's more massive, if it's more made of more stuff. So it'd be more difficult for me to stop a skateboard moving towards me than it would be to stop a semi-truck, even if they're moving at the same speed, because the semi-truck is more massive. So mass is simply a measurement of the amount of inertia we have. Symbol for mass, we have a lowercase m, and our standard units for mass are the kilogram. Okay, so this is one of our base units, one of the base fundamental properties of all objects. It's how much stuff it's made of, which is kilograms. Okay, so mass, or the amount of stuff an object is made up, is what really gives that object that inertia, which makes it want to stay at rest or maintain a constant speed if it's set in motion. All right, so let's take a look at our example. So let's say I have 3 pucks shown here in A, B, and C. They're both the same hockey puck, just noted they're going at different speeds. So in A, they're going at 2 meters per second, B 4, and C 6 meters per second. So it says here, rank the forces needed to keep them moving from greatest to least. So applying Newton's first law, what we got to understand is that an object in motion wants to stay in motion. All right, so if this thing is already in motion, is there a force really necessary to keep it moving? In that case, the answer there is no. In this case, there is really no force needed to keep them moving. So what I could say here is, well, I guess we could look at this as that they're all equal. A equals B, which also equals C. But really in this case for A, there is no force necessary. Okay. All right, now if I want to talk about ranking the forces needed to stop them in the same amount of time. So understanding that all these hockey pucks have the same mass. They're all identical hockey pucks, but what's happening is that they're moving at a different speed. So if I wanted to stop these things from moving, well then all of a sudden there would be a force that's necessary. If they're already moving, in order to stop it, I would have to apply a force back against it. All right, so obviously I'm stopping the same hockey puck. So if they were moving at the same speed, then obviously it'd be required the same force to stop them. But since C is moving at a greater speed, okay, it would take more effort to stop that because not only does it have some mass to it, but it's got a little bit more oomph to it because of how fast it's moving. So then, based on the speed, B would probably be next and then followed by A. Okay, so first part here is just applying Newton's first law that if it's already in motion, there really is no force necessary to keep it moving. But if I were going to stop it, then I want to look at yet not only how much oomph it has, how much inertia, but then also considering the speed. All right, now it says to rank the inertia of these carts from greatest to least. So similar problem. So why don't you pause and give this one a shot. All right, so there you go. Based on what we talked about in the last example, if I want to think about the inertia, obviously we're looking at the mass of an object. So in terms of which one's more massive, we have the 1 kilogram object versus the 2 versus the 3 versus the 4. But at the same time, we see the speeds. Okay. So what I did here is what I consider is if I look at mass and speed, what I did was just multiply together, just to give us a sense of kind of what's going on here. So 4 meters per second times 1 kilogram, give me like an overall oomph of 4 units. Here, multiply those two together, we get 6, 4.5, and 4. So let's see here that I have kind of a middle of the road in terms of mass, but also something that's moving a little bit quicker. So this would be a little bit harder to stop than it would the other ones. So yes, even though this one is a little bit more massive, it's not moving as fast, so it wouldn't be as hard to stop it as it would say this one. So in terms of the order, I would say B, C, and then notice A and D, I both get a value of 4 there, so those inertias would probably be about the same. So again, what we're looking at here is this idea of inertia, which looks at the mass of an object, but also looking at these examples kind of considers the speed at which they're moving to.